I'm sorry.
Okay. Right, so the goal of this is to turn this fraction into two fractions. That's it. So it's a bit like if someone said, if I have 7 over 12, and I want to write this as fractions something over 4 plus something over 3, what could I do?
Divide.
Well, you have to think deeply first.
Obviously think very deeply.
It would be 1 and 1.
Or 2.
No, 3.5.
Why isn't it 1 and 1?
It can be 2 and
It's 1 and 1.
Yeah, it's 1 and 1.
Thank you, everyone. Doubting.
Yep, because that'd be 3 12s, 4 12s, 1 and 1. So this is the same process as we're trying to do, we're just doing it with a more complicated thing. We need, first of all, to think about what two things would multiply
You need to
and form a
factorize
com-
the denominator.
form a common denominator. Yeah, so this is our common denominator. What two things multiply to form it? Or what? How do we
X
Do.
plus 3 and X minus.
Yeah, so how do I factorize this? You could do a little factorization underneath here. X and X, 3 and 2, plus and minus, fantastic.
Yay.
We have X minus 2 could be one, and X plus 3 could be the other, all right? And all we need to figure out is what would go on top of these two fractions. That's it.
Interesting.
Interesting. That is an interesting one.
Okay? So, does that make sense? No?
No, yes.
Yeah, okay. So we haven't done anything yet. We just have, well, we factorized this to form two things that multiply. So same as the 4 and 3 multiply to give the 12. These two multiply to give this. But it's not as easy to just logic out the 1 and 1 here. What we could do then is let the right hand side here equal the left hand side. So if these are, if you went to say, right, I want to add these two together, what would you do? You'd get a common denominator, which we already kind of know, as x squared plus x minus 6, yeah? We get the common denominator and we like multiply this by x plus 3. Yeah? And multiply this by x plus 2.
Minus.
X minus 2, yeah. And what we have now is equivalency. We can say that this is equal to that, isn't it?
Yeah.
So we can just solve now the numerators. This bit is equal to this bit. So if I multiply out the numerator only, I get ax plus 3a's, not equal, plus bx minus 2b is equal to 7x plus 1. Yeah? So I've just multiplied this by a and this by b. Now I can see that all the x's must equal, yeah?
So it must be 7.
So I could say over here, yeah, a plus b from the right hand side is equal to 7 from the left hand side. That must be true if these two things are equal. And I can also say that 1 plus 3a minus 1 is equal to 3a minus 2b.
Oh, so we're doing simultaneous equations. Boy.
So we've got a simultaneous equation. You can solve it by substitution or elimination. Multiply the top line by 2 is where I would go first.
Uncle, did you get this another way?
Actually, we learned about this before.
I like logic.
Yeah, I would have done the same rather than this.
So we have the b's cancel. What's a going to be?
5.
Yep. 3.
A is 3. Wow.
Oh, very cool.
And then if a is 3, what's b?
4.
4.
Yay. Yay.
Yeah, I got it.
Congratulations. This was 3 and this was 4. And that is how we do it.
But then, like, for partial fractions, does the denominator always like equal to two fractions? Or can it be like a cubic denominator?
It can be cubic, and then you have to be ABC. The reason partial fractions is, when we go to do integration, it's, as you may know, Aidan, it's very easy to integrate something like this.
Yeah.
It's very difficult to integrate something like this. So that's why we want them as partial fractions. So if it's cubic, we want linear, linear, linear in the denominator.
That's so smart.
Isn't it? Right, you do so.